This is lecture 18 of M.223. So, in last session what we have seen is the notion of differentiability of a function. So, if f is a function from u to r, u subset of r, and in the point we fix a point a belongs to u, we say that this function f is differentiable at this point a if some limit exists. So, what is it? Limit h goes to 0, f of a plus h minus f of a by h. If this limit exists, then we say that this function f is differentiable at this a, and this limit we are calling it as the derivative of f at a, and we denote by this symbol. We read this as f dash of a. And we have seen some examples of differentiable functions, and we have also seen some constructions in the sense, suppose I take two differentiable functions f comma g from u to r. Forget about differentiability or any other structure on u. We have two functions, one can talk about, because they are taking values in r, one can talk about their sum f plus g, it's a map from u to r, or f minus g, it's a map from u to r again, or f dot g, again a map from u to r. We have seen before that if f and g are differentiable on u or at a point in u, then f plus g, f minus g, f times g, these are differentiable on u if f and u they are differentiable, or at a point a if this differentiability is only at that point. Then we have seen one more construction. What is it? Suppose f from u to r is differentiable, and this f takes values in r minus 0. F of u is contained in r minus 0. In another way we say that f is nowhere vanishing. F of u, f of a point of in u is non-zero for any point. Then we have seen that this 1 by f function is differentiable on u, and not just differentiability, we have also seen what is the derivative. See, differentiability means what? This limit exists. We have said something more than that existence of differentiability. We have said what is the derivative. If I take a point a belongs to u, we know what is f plus g dash of a, or f minus g dash of a, or f times g dash of a, or 1 by f dash of a. All these we have seen. Now, see, what we have done in continuous functions is a similar thing, but we have done something extra in case of continuous functions. What is it? Suppose I take two functions, u to r is a map f, v to r we are writing as g. Suppose we take two functions, and suppose we know that f of u is contained in v, then we have said there is something called composition, which we denote by this symbol g compose f is a map from u to r. How is it defined? I take some element a. If I take some element a belongs to u, a is element here, f of a is element in r, but we have assumed that f of u is subset of v. So, f of a is an element of v now. So, one can take the value of g at that point, and that gives an element in r that we are writing as g of f of a. We have seen before in case of continuous functions that if I take two functions that are continuous and with this property, then this, the so called composition, is a continuous function. So, we can try to do the same thing for differentiability. Suppose f and g are differentiable and we have this condition, then do we know that g compose f is differentiable? Not just that, we want to also, I mean, see, in case of these four constructions, we have seen the differentiability, and not just that, we also know what is the derivative. So, here we also want to know what is the derivative. I mean, if it is differentiable, we have not proved that it is differentiable yet, we will do that. Now, so how do I check that this is differentiable and all? Before we go to that, I want to mention an alternative description for derivative of f at a. This candidate is motivated when we start with the assumption that f is continuous u to r, and see we have mentioned before that one description of continuity of f at a point A is this: x goes to A, f of x is equal to f of A. Then we have said for some other purposes we want to move the reference point from A to 0, then we have said this is same thing as saying that limit h goes to 0, f of A plus h is equal to f of A. This is what we have said. So these two are actually equivalent statements. Then from here we have come across this candidate. Then we have said that if that limit exists, then we say f is differentiable at that point A, and this limit is the derivative of f at A. Now sometimes it is useful to start at this point instead of this point. It is useful to start at this point. Now an obvious question is, okay, for this starting point we got this candidate, and if this limit exists we called it differentiable at A. Now suppose we start here, what do we get? I am leaving it to you as an exercise, that if I start here and do the same thing that we have done for this starting point, what we get is the following. We get that limit x goes to A, f of x minus f of A by x minus A. This is where we reach if you do the same thing. Then if this limit exists, then we have to say that it is differentiable, and we denote, again we are denoting by f dash of A. These are actually same. Check for yourself that this limit before writing this limit is equal to this limit if they exist. If one of them exists, then other exists, and then they are same. So this is useful in some places. Similarly, this is useful in some other places. Depending on the necessity, we use either this candidate or this candidate. Both are same. Now again we'll come back to this composition situation. We are trying to see, suppose f and g are differentiable, and this it has this property, then g compose f is g compose f differentiable at a point A. So for that what we need to do is following. We need to check that whether some limit exists or not. Limit h goes to 0, g compose f of A plus h minus g compose f of A by h, if this exists or not. Let us write down what is this. This by definition, this is same thing as g of f of A plus h minus g of f of A by h. Now see, if you recall how we have proved differentiability of these four functions, then you will realize that in most of the cases, or maybe in all cases, that at least the numerator it reminds us of some differentiability. Let me say, in case of say f times g, fg of fg dash of A, what we had is limit h goes to 0, fg of A plus h minus fg of A by h. So this we have seen as f times A plus h times g times A plus h. There is of course a limit here. Limit h goes to 0 minus f times A, g times A by h. This reminds us that one can talk about, see, these two has a this component in these two reminds us that we should be looking at differentiability of f at this point A, or these two should remind differentiability of g at that point A. So it gives some idea of what to do. Then what did we do? We add and subtract some term, some particular term. Then this term that we have added here, which I have erased, this is something as f dash of something into g, and this is something as j dash of something into that. So this usually numerator gives some idea of what to do. Here there is a small problem. I don't know how to proceed. There is a g of f of A plus h minus g of f of A. Maybe first let me remove this. So So now we have this candidate. The question is how do I fix it? How do I turn this into something that I already know? Observe that look at this derivative, f of x minus f of a by x minus a is f dash of a. Here you have f of a plus h minus f of a, but in the denominator there is it's not the case. So one obvious thing to do is the following: maybe multiply and divide by f of a plus h minus f of a minus f of a. But can I always do that? I mean in the sense that f of a plus h minus f of a, because if it is continuous at a, that should go to 0. So I don't know whether I'll be able to write down that in the denominator. I don't know whether it makes sense or not. Does it make sense? You think about it. So what to do is we will try to so now the idea is clear. We are trying to do this following: f of a plus h minus f of a, f of a plus h minus f of a. We are trying to do something like this. But suppose suppose if it is a constant function, then this is equal. So we are trying to do something like 1 by 0 or 0 by 0, which doesn't make sense. For me it doesn't make sense. So I am not really supposed to do something like this. But just suppose that this is not 0 for any point. But see, limit h goes to 0, this is always 0, because if is continuous at a, limit h goes to 0, this is always 0. But let us assume that at least when we are taking a particular point, that these two are not same. In that case, one can consider this, that this is what g of f of a plus h minus g of f of a by this. So let me write that down. See, this is not this should not be seen as a real proof. This is only some idea. So g of f of a plus h minus g of f of a by f of a plus h minus f of a. Now what? Okay, I have kept this here. Then maybe I should put it here. So this is something as times f of a plus h minus f of a. This is plus by h. So this reminds us that we should be thinking of differentiability of g at f of a. Observe that what you have written here: differentiability of f at this point a, fx minus fa by x minus a as x goes to a is f dash of a. Here you have g of f of a plus h minus g of f of a by f of a plus h minus f of a. This should remind you that we are trying to do, we are somewhat close to the case that g dash of f of a. And what about this? This you already know, this is nothing special, this is plus. So this you already know, this is f dash of a. Now see, some things need to be fixed here. First thing, here I am writing x goes to a, here I am writing h goes to 0. How are they relevant? Observe that if h goes to 0, then f of a plus h goes to f of a, right? I hope you remember that. H goes to 0, f of a plus h minus f of a is same. H goes to 0, f of a plus h goes to f of a. So this I can replace by in this sense, that I can simply write limit h goes to 0. This is same thing as limit f of a plus h goes to f of a, this thing, and we know this is something as g dash of f of a. For this we will leave it as it is, that this candidate should remind you that we are dealing with f dash of a. So with not very precise meanings for each step, we reach at a conclusion that maybe, see, some things need to be explained, which may not have an explanation, but we got to a place where it looks like that g composite is differentiable at a point a, and the derivative is g dash of f a times f dash of a. So it looks like this is the case, but as I said, some things need to be explained. Maybe suppose if it is continuous, if it is constant function, then these are same. I cannot do this. I cannot do this thing. If that is constant function, then this is also 0. So there is really nothing to do. But still, we will try to give a reasonable proof. So now we have that we have a candidate, at least, that g dash of f a times f dash of a. We will try to prove this. Suppose we are doing in this sense, there seems to be some gaps. So we will look for an alternative explanation. As an exercise, you can try to fix these arguments or give some more explanation, so that this explanation becomes sensible. In any case, we are going to see other proof for this. So to prove this, we use some alternative result, and let us see that now. So observe that differentiability of f at a point A has something to do with this limit, h goes to 0, f a plus h minus f of a by h. Again, as I said, this is plus. Now see, observe that this thing is a function of h. So and this function is not from u to r, right? It is a function of some neighborhood of 0, right? This is a function from not from u to r, because h is not an element of u. H is going to 0. So this is some neighborhood of 0, say something minus delta something like that to r. This candidate is a function of function from some neighborhood of 0 to r. So suppose for the function f and after fixing a point A, suppose there is a map g from maybe same neighborhood minus delta to r, such that f of a plus h minus f of a is equal to h times g of h in this neighborhood. Suppose this is the case, and suppose I know that this is continuous at 0 is an element here. So I am just asking that g is continuous at 0, which means what? Limit h goes to 0, g of h is equal to g of 0. First of all, this exists, and that is same thing as g of 0. Suppose we have this condition, then what happens? I can just pull it here and write down f a plus h minus f of a by h, this is equal to g of h. Now this is function of h, this is function of h. I can take limit on both sides. Whenever I can do something, I will just do it. So this is something as limit h goes to 0, g of h. Just now we have said that g is continuous at 0, so this limit exists, which means that this limit exists, and this limit g is continuous at 0, so this is something as g of 0. So this says this limit exists, which is other sense to, which is in other words, f is differentiable at a, and f dash of a is equal to g of 0. So what we will do now? Given a function f from u to r and a point a belongs to u, suppose there is a function g from some neighborhood of 0 to r satisfying this condition, f a plus h minus f a is h times g h, then and we are assuming g is continuous at 0, then f is differentiable at a and f dash of a simply g of 0. Now the result that I said that will be useful is the following. It is just the converse of this. Suppose f from u to r and a is some point in u. If f is differentiable at a, then it says there is a map from some neighborhood of 0, not necessarily in this fashion, some neighborhood of 0 such that G is continuous at 0 and f of a plus h minus f of a is equal to h times g of h in the neighborhood, in this neighborhood, wherever this makes sense. And further, as I have said before, f dash of a is equal to g of 0. This result, whatever I have said here, it goes by the name of what is called characteristic lemma. I cannot remember the spelling correctly, so check in Google this characteristic lemma. Now see, this candidate is useful when we are trying to do some computations. So this we are doing when our definition of differentiability is this. Suppose our definition of differentiability is something limit x goes to a, fx minus fa by x minus a. Suppose this is our definition. This is what we want to use. Then we need to have a similar thing, right? We need to have a similar function g. Now g is a function from u to r. G is a function from u to r such that this candidate is fx minus fa is equal to x minus a times g of x, not necessarily on whole of u, maybe in subset of u. Then we have this candidate. So if f is differentiable at a point a, then for that particular point there is a map. See, this depends on a. There is no reason why for every a single g should occur. There is no reason. I don't know why it should be the case. What I know is, if I fix a point a belongs to u, then there is a ga, there is a function continuous at a belongs to u, continuous at a, such that we have this condition. Now what I mean, now this is, I will use this formation to prove that this function g compose f is differentiable at this point a. How do I do that? So let us write down. See, one very bad notation here that we have used is we are using ga for the and we are using ga, and previously also we used g compose f. So let me change this into, say, h. No, not h is also bad notation. Theta, yeah, something like that. Theta is fine. Theta a is in the domain of the function f. For that fixed element, there is a map continuous at this point a, satisfying this condition. Now let us go back to the composition thing. What we have is, we have two functions. This is g, this is f, and we are fixing a point a in u. As I said, because f is differentiable at this point a, there is a function theta a from u to r such that not g, fx minus fa is equal to x minus a times theta a, or maybe theta of x for every x belongs to on u or maybe a subset of u. Similarly, g is differentiable at f of a. F of a is now a map in u v. So for this also there should be some now I cannot use theta, I should use maybe phi, not u, v to r or maybe subset of v to r, such that g of see, I want to use a different coordinate here. You will come to know why I am using. Here I am using x for the function f, here I will use y for the function g. So gy minus g of what we are doing, we are trying to do for f of a, right. So here we did for a, so we have written f of a, here we are doing for f of a, so we will write f of a. This is equal to, look at the point, this is x minus a, so what do you think we should be writing here? Y minus f of a. I will just pull it, there is no place, times phi a, not a, this is f of a, phi a times y for every y belongs to maybe some subset of v. So, this is the case for a we have this function theta a, for f of a we have the function phi f of a. Now what? This is true for every y belongs to v. In particular, for y is equal to f of x for some x in u. Suppose this is the case, then also this should be true. So let us write that down. So g of f of x minus g of f of a. See, I am just replacing y with f of x. I am not doing anything else. Here also I should replace y with f of x. So this is equal to f of x minus f of a times this I should replace with y is replaced by f of x. So times phi f a of f of x. See, maybe you can just you can just remove this f a. Once you know that this function is dependent on f a, then you can stop writing this. But at least for some time you keep this notation, so that you will remember that this is not the single function that works for every element on the domain. It depends on the point that we have chosen. Now what I have said, or yeah, if it's differentiable, so we have this equality. So I can replace fx minus fa by this candidate. So when I can do something, I will just simply do it. So this is something as x minus a times, what is this? Theta a of x. Theta a of x times, there is again this phi thing, phi f of a times f of x. Right now, so this I will change it slightly. G of f of x is same thing as g compose f of x. So I will just write that g compose f of x minus g compose f of a is equal to x minus a times theta a times phi f a compose f at x. Right, that's what I have written here. Theta a of x, this is the product. So product of two functions is theta a times x times this at x. That's what I have written here. So for g compose f, for fixed a, I have this function such that g compose f x minus g compose f a is x minus a times this. So that says, as I mentioned before, g compose f is differentiable and the derivative g compose f dash a is this evaluated at a. So theta a times phi f a compose f at a. What is this? Theta a of a times phi f a compose f of a. So I am just writing as f of a. What is this? I have said before that if f is differentiable at this point a, then there is a map theta a from u to r with this property, and theta a of a is f dash of a. So here I should replace this with f dash of a. Again, for the function g, we have said there is a map phi a such that it has this property, and phi a of f of a is a g dash of f of a. So here I am replacing this with g dash of f of a. So what does this say? Suppose I have two functions which are composable and both are differentiable, then their composition is differentiable with this derivative times f dash of a. This result you might have already seen, you might have used without knowing the proof. Now we know the proof. G compose f dash a is a g dash of f a. We will write down this clearly. G dash of f a times f dash of a. This formula can be used to prove that some function is differentiable, and we know the derivative also. So that is about when we are trying to prove this, we have mentioned some result also, that is this character that is lemma, and this says given two functions that are differentiable and they are composable, then composition is differentiable and this is the derivative. Now let us do some example. In previous session what we have seen is that suppose I take a continuous function, that is a constant, then continuous function is already constant. Suppose I take a constant function from U to R, then this is differentiable and the derivative is 0. How did I do that? So this limit h goes to 0, f of a plus h minus f of a by h. Suppose if it is constant function, then these two are the same irrespective of what h you choose. So this is a 0 function, 0 by h is 0. So this is we are taking limit of some 0 function, so we should be getting 0. So f dash of a is 0 for every a belongs to 0. If I know that function is a constant function, then the derivative is 0. Okay. Now we will do one more example. In this case, we were asking that f is a constant function on the whole domain, then we have said that f dash is 0 for every a belongs to u. Let us do one more example where f is not constant on the whole domain, maybe it is constant on a subset of the domain. So maybe let us take the following example. F is from u to r. We are looking for some example where on a subset of u if is constant. So let us take some let us fix some value for the domain u. So u is minus 4 comma 4, or maybe some open set containing minus 4 comma 4. Then we are saying on this domain minus 2 comma 2, we are giving that value to be 0, it is constant. Then from 2 comma 4 we are asking that it takes this value. I am assuming you know whenever I write draw some line like this, you should know what is how to represent that I am assuming you know whenever I write some line like this, I am assuming you know how to represent that as a function. And what about this between minus 4 comma minus 2, I am just taking another function. So f takes value 0 here, it takes this form and takes this form in the corresponding thing. Now so let us write down that function. F x is equal to 0 whenever x belongs to minus 2 comma 2, and from 2 to 4 it is taking this value. Suppose this point is 0 point, suppose it is 0, then this line denotes that we are talking about y is equal to x, but here we are changing it by 2. So now for x belongs to 2 comma 4, the function is x minus 2. Observe, at 2 we have 2 minus 2 0, at 4 maybe it is 2, so it is like that. It is supposed to be x, y x, this if I write if I draw some line like this, if I draw some line like this, this is y x is equal to x. If it is taking 0 value at 0, but if you are writing say to the right side, so say 2 it is 0, it is x minus 2, you are shifting that to the right hand side, so you get a minus 2 here, that is what I have written here. Now what about this? This function is I am assuming you know this but I am still repeating. So this thing is y x is equal to y is equal to minus x, this thing is y is equal to x, this is y is equal to minus x, right. If you see, for 1 it is taking the value 1, for minus 1 it is taking the value 1, so it is this function. And then observe, we are also shifting it to the left hand side, so for x belongs to minus 4 and minus 2, it should be minus x, should we be writing plus 2 or minus 2? Observe, for minus 2 we are getting the value 0, so if I put, see, let us try and put plus 2 here, then what about f of minus 2? this is minus of minus is plus, 2 plus 2 is 4. So, this is wrong, it should be minus x minus 2. So, let us change this. So this is the function for which this is the corresponding graph. Now, this is all not relevant. So, let me remove this. Maybe I will leave it as it is, that should be okay. Now, what? Now, we are checking for, we do not know whether this is differentiable or not. We just have a function and it is easily to be continuous. I am assuming you have seen similar example when we have done continuity. Now, we are trying to check whether this is differentiable at some point. Say let us fix a point, minus 1. Minus 1 belongs to the domain. Let us check if this function f is differentiable at this point minus 1. For that, we need to do what? We need to check if this limit exists, plus h minus f of minus 1 by h. The question is whether this limit exists or not. If it exists, what is the corresponding limit? Now, we need to compute this limit. Observe that f of minus 1 is 0, minus 1 is here. So, f of minus 1 is 0. So, I can just write limit h goes to 0, f of minus 1 plus h by h. This is what we are supposed to compute. Now, suppose this is equal to a. What we need to do is, we need to prove that if I fix epsilon positive, there is a delta positive such that whenever x is mod x is less than delta, we should have f of minus 1 plus x by x minus a is less than epsilon. This is what we need to show. Observe the following, that this f, the whatever I have defined here, in a neighborhood around minus 1, it is actually taking value 0. So, maybe if I choose a nice neighborhood, then this is actually 0 function. Let us do that now. This is actually 0 function. Then I am claiming that this a is actually 0. So, let us just check whether that is the case or not. So, we are trying to see that given epsilon positive, there is delta positive such that whenever mod x is less than delta, this is less than epsilon. And moreover, I am saying, what I am saying is this, minus plus x is actually equal to 0. What I know is just that f is 0 from minus 2 to 2. So, suppose minus 1 plus x, suppose this belongs to minus 2 comma 2, then I know for sure that this is 0. This is same thing as saying that x belongs to, okay, let me do one more step. So, minus 2 less than minus 1 plus x less than 2. This is same thing as saying, I am just adding 1 on both sides, minus 1 less than x less than 3. So, if x belongs to minus 1 comma 3, then I know for sure that this is 0. If this is 0, then the condition is already satisfied, because epsilon is already positive. Okay. So, the delta that I am fixing here is say half. So, whenever x is such that mod x is less than half, this is something as saying minus half is less than x less than half. Whenever x is in this interval, it is already in this interval. So, and then if it is here, it satisfies this property. If it is here, it is 0. If it is here, this is 0. So this is actually 0 function irrespective of what x you choose. So, this says that this thing is this limit is actually 0. So, our guess is correct, this is simply 0. So, this says the function f that we have described here is differentiable at this point minus 1 and the derivative is 0. So, it should suggest something, that even though this function f is not constant on the whole domain, for f of minus 1 is 0, 0 is not really important point. F is constant on a neighborhood around minus 1, minus 2 to come to the neighborhood around minus 1, on which f is constant. For that, that's what you have used, and prove that f dash of minus 1 is if is differentiable and f dash of minus 1 is 0. Maybe one more thing that I want to explain here is to check the maybe one more thing that we can do is, let us check whether f is differentiable at this point minus 2 and 2. So let us take so now we are checking differentiability of f at minus 2. Further we need to check whether this limit exists or not. F of let us check at 2, f of 2 plus h minus f of 2 by h, but f of 2 is 0, so this is gone. Now we are looking for this limit, we are looking for this limit. Suppose this limit exists, suppose this is a, then we need to then the condition is the following: for any sequence that converges to 0, we should have f of 2 plus xn by xn should go to the a that we have fixed here. This is a. So let us take a sequence, say 1 by n that goes to 0. Let us evaluate this at 1 by n. So we have f of 2 plus 1 by n by 1 by n. Observe that the function f for values to the right side of 2 plus 1 by n is to the right side of 2. For this we have this description, this is x minus 2. So f of 2 plus 1 by n is 2 plus 1 by n minus 2. This 1 by n I am writing as it is. So this is gets cancelled, 1 by n by 1 by n, this gets cancelled, this is 1. So this thing is actually constant function, this is actually constant for any n. So this should converge to 1, nice. So maybe a is equal to 1, we do not know, but for the sequence that we have taken we got this to be 1. And there are other sequences that goes to 0, and the other example that the other sequence that we can think of is minus 1 by n. Minus 1 by n also goes to 0. Let us try to evaluate this at minus 1. Let us try to evaluate this at minus 1 by n. So now what do we have? F of 2, instead of xn we are writing minus 1 by n. 2 minus 1 by n by instead of xn we should be writing minus 1 by n, minus 1 by n. Now what? 2 minus 1 by n is to the left side of 2, so it's here, and it is of course less than of course greater than minus 2. So we should be looking at this description. So this thing f of 2 minus 1 by n is 0, because 2 minus 1 by n is to the left side of 2 and it is greater than minus 2. So this is 0 by minus 1 by n, whatever it is, so it is 0. So this function is 0, this value is 0 for any n, so it should converge to 0. So there seems to be some problem here. For one sequence we are getting that this limit is 1, for the other sequence we are getting the limit as 0. So this limit, it means this limit does not exist, which means the f that we have mentioned here is not differentiable at 2. How did we do that? How did we prove that? We took two sequences, 1 by n and minus 1 by n, both of them are converging to 0, but this thing converges to 1 if you are taking one sequence, it comes to 0 if you are taking another sequence. So there is no consistency. This says f is not differentiable at 2. The same idea can be used to prove that f is not differentiable at minus 2. So the best we can say is, for this function in the neighborhood minus 2 comma 2, at every element in this neighborhood f is differentiable and the derivative is 0. So this suggests the following definition: a function f from u to r is said to be locally constant at a point a belongs to u if there is a neighborhood say maybe we can say there is a delta positive such that a minus delta and a plus delta are contained in U and f is constant in this neighborhood, a minus delta and a plus delta. I do not know whether this is standard terminology or not, but what I am saying is we say this function is locally constant at this point A if there is a element, if there is a delta positive such that this neighborhood is contained in U and f is constant in that neighborhood. So this fits into this, so the previous example fits into that description. So this function is locally constant at every point in this in minus 2 comma 2. Now, so instead of taking the specific example, let us try to see whether if I study a locally constant function, if I study a function that locally constant at a point A, do I know that the corresponding derivative is 0? Suppose if it is locally constant at A belongs to U, does it say anything about the derivative? Is it 0? See, here I am assuming that f is differentiable already. Here we did not assume f is differentiable, and we have proved that at these 2 points it is not differentiable. But for this result we are assuming that f is differentiable, and then we are asking for the derivative of f at A, whether this is 0 or whether it is not 0, something like that. So now how do we prove this? How do we write down the limit description for the f dash of A? Limit h goes to 0 f of a plus h minus f of a by h. So we are expecting that the derivative exists. So this limit exists. We are expecting that this is 0. So for that we need to prove that given epsilon positive, there should be delta positive such that whenever mod x is less than delta, this evaluated at x minus 0 should be less than epsilon. F of a plus h minus f of a by h should be less than epsilon when this h is equal to x. Here we are replacing h by x. Now see, I used it was not intentional, but I used same delta in both cases. Here also I use the same delta. Maybe one can use this delta to produce this delta. Okay, let us check if this a plus x is in this interval. In that case, f of a plus x is same thing as f of a because it is already in that interval. So is a plus x belongs to what is this interval? A minus delta and a plus delta. Whenever x is whenever mod x is less than delta, do we have this? Let us check that. So this is what a minus delta less than a plus x less than a plus delta. This is what we need to have, and we have a at 3 places with same sign. So this can go. So I will just remove that. So see, this is same thing as saying that mod x is less than delta, right? That's what we have here. So whenever mod x is less than delta, we have this case. Then the next thing that you do is you just add a at 3 places, then you get this. Whenever a plus x is in this domain, f of a plus x is the same thing as f of a. So this is actually 0. So irrespective of what point you choose, this is actually the numerator is a 0 function. So epsilon is greater than 0. So this condition is satisfied vacuously. So this says that the derivative of f at this point a is 0. So whenever f is locally constant at a, f dash of a is 0. See, we are not saying that any function that is locally constant is differentiable and the derivative is 0. No, that is not what we are saying. We are saying if I have a differentiable function and at a point a in the domain of that function, if from u to r is differentiable and a belongs to u, if f is differentiable and it's locally constant at this point A, then f dash of A is 0. This is what we are saying. Okay. So this says that local description of a function at this point A is determining the derivative at that point. So previously we have seen the local description that being constant at this point A, there is no point set containing that, on which f is constant, then we have seen this is 0. So let us do a similar description, not the constant one, let us do something else. So let us fix a function f from u to r and a point A belongs to u. Again the same thing, for this element A there is a delta positive such that A minus delta and A plus delta is contained in u, and f restricted to this domain is special in some sense. See, suppose it is constant, that is what we have done before. Now what we are asking here is that it is not constant. What we are asking is, this is completely determined as per the order, whatever it might mean, determined in the following, determined by the value at A, in the sense there is some relation between this and this. More precisely, what we have is that for every x in this domain A minus delta and A plus delta, what we have is f of x f of A. So this is what I mean when I say the value of f at this point is determining when we are dealing with this the order property. This determines behavior of f on this domain in this sense. For every x in this domain we should have this. If this is case, then we call f to be, we should be calling f to be locally something. Here we are calling f to be locally minimum at this A, or A is the point of local minimum for the function f. So let me write down that local minimum. Similarly, suppose I have this condition, then I am sure you know what is this, or you can guess the name. So if for a function f, given a function f for this point A, if there is a delta positive such that this domain is contained in u, and f restricted to this is determined by this element either in this way or in this way, they have corresponding names. If it is this, then A is called a point of local minimum. If it is this, then A is called point of local maximum. So see, previously also we have said that the local description is determining the derivative. So here we need to, here we expect the same thing, that suppose it is local minimum. Can I say anything about the corresponding derivative? What happens to f dash of A? If A is point of local minimum, what happens to f dash of A if A is of local maximum? Now, so the question, we do not even know how to proceed further. So let us write down whatever we know for the derivative. If I take a function f from u to r, that is differentiable at this point A belongs to u. Let us write down whatever we know. So one thing we have seen in this session is that there is a function g r such that f of x minus f of A is equal to x minus A times g of x, and the g is continuous at this point A. So this is what we have, and as I said, this function depends on the point that you have chosen. It is not necessary that there is a single function that works for every point. This is what we know. We don't know anything more than that. Now let us assume that this point is a local minimum point for this function. Maybe writing these two at the same place may be creating some confusion. So let me just pull it. Yeah. So this is the setup. So this is the setup, and because f is differentiable at this point A, there is a map G satisfying this property. Now what we have is there is a delta positive such that on a minus delta and a plus delta we have some condition. As I said, A is point of local minimum. This means for every x belongs to a minus delta and a plus delta, we should have f of x as a local minimum, right. So, it should be this. Now, see, this is true for every x in U. In particular, for x in this interval, this should be true, and for x in this interval we have this property. So, f x minus f a is positive. This says x minus a times g a of x is positive, greater than or equal to 0. Okay, now, so we have this minus delta here, plus delta here, v here. So we have this for every x in for every x here. Suppose x is we take some x here, x is less than a, then also this is true. So what does it say? If x is less than a, x minus a is negative, but this product is non-negative. This suggests that GA of x is less than or equal to 0. Suppose I take x here, then also this should be true. If I take x here, then x minus a is positive, product of two elements are positive, one of them is positive, this suggests that this is positive. So G A of x is positive. Okay, now G is continuous at this point A, and we have these two inequalities, that G x is less than or equal to 0, G x is greater than or equal to 0. Just the continuity of G at the point A conclude that G A of A is 0. By the way, what is G of A? We have seen before that if the function G, where is it? Yeah, if the function G A satisfies with this property, then G A evaluated at the point A is derivative of f at A. So this says what? This implies f dash of A is 0, right. Just the continuity of the function G A at the point A conclude that the derivative is 0. So let me just quickly recall whatever we have done, just this part, not from the beginning. So we have a function f, we know that it is differentiable, and we have a point A belongs to U, that is the point of local minimum. That means this, there is a delta positive such that for every x here we have this property. Now we have used the previous result that says if I have a function f that differentiable at a point A, then there is a continuous function from U to R such that we have this property. Then because f x is greater than or equal to f a for every x here, this is positive. This implies x minus a times G A of x is positive. Now x can be anywhere here between a minus delta and a plus delta, that is what this means, right. Now suppose and we have the point A here, suppose x is to the left side of A, this means x minus a is positive, this imply that this thing should be should be negative. Okay, x minus x is to the left side of A, this is negative, the product is positive, this implies this is negative, that is what I have written here. Similarly, if x is here, then the similar conclusion, similar justification says that this is this. Now G is continuous at 0, so these two should imply G of A is 0, but G of A is simply f dash of A. So this says if f is differentiable and A is point of local minimum, this implies f dash of A is 0. Suppose we start with the assumption that f is a point, this A is point of local maximum for the function f, then what do we have? Instead of this we have this less than or equal to, right, the same thing. Then this product is like this, right, this is negative, so this is negative. Again the same thing, that if I take x here, x minus a is negative, this product is negative, so this has to be positive. So just the same, if previously if x is here we get this situation, now if x is here we get this situation. Similarly, if x is here, previously we got this situation, previously we got this situation, now if x is here we get this situation. In any case we have both situations, and again the same thing, continuity of g at the point A imply that g of a is 0, but g of a is f dash of a. So this is again same thing, take a differentiable function, take a point A that is locally I have written m, it is not very clear whether it is minimum or maximum. So in both cases we have this, so this is not a mistake. Local minimum or local maximum, in any case f dash of a is 0. Now, so we are going step by step. Previously we have said that if a function is constant, then the derivative is 0 at every point. Then we have said if it is locally constant, then the derivative is again 0. Then we have said if it is one to local minimum or a local maximum, the derivative is 0. Okay, let us take a function f, and suppose it is defined on this domain, and suppose a is here. Suppose it is local minimum. You should be thinking it as something like this. This point is local minimum, and if it is local maximum, you should be thinking something like that. Now let us increase the complexity just one step above. Suppose let us take 2 points in the domain. This is the domain U, and let us take the point A, and let us take the point B. Suppose, see, if f is constant in the whole domain, if a is equal to fb, then you know for every point the derivative is 0. We are not asking that. What we are asking is the simple thing. There are 2 points that take same value. See fa, these are same value. This is not a straight line, but I'll assume that this is straight line. If they are taking same value, and I know that it is differentiable, so it has to be continuous. So there should be some way to connect these two, either in this way or some other way. Then suppose it is this way, there may be some point which looks like local minimum, whatever we have drawn here, or it can be of this form, in which case there is a local maximum, or maybe it is very bad behaving, but still there should be some way to connect fa and fb, and because they are same, one possibility is that it is just constant, other possibility is this, other possibility is this, there are many possibilities. In any case, in 3 cases that we know, suppose there is a local minimum point, then you know that its derivative is 0. Suppose there is a local maximum point, then its derivative is 0. We assume that something like that will happen. So just with this assumption that there are 2 points a comma b belongs to U, such that f of a is equal to f of b, f is differentiable, that I am not repeating. We are saying there is a point c belongs to U, c belongs to a comma b, such that f dash of c is 0. See, suppose you have suppose there is a point of local minimum. We don't know whether there exists something or not, but it looks like that is one of the possibilities. It may not be the case every time, but if f of a is same thing as f of b, and you are supposed to connect these two, this is one way, this is one way, this is one way. We can write only 3 ways, maybe some more, maybe reducing the height, something like that. In any case, it looks like there is a point of local minimum or local maximum, but that is not what we are saying. What we are saying is f dash of c is 0. This is what we are trying to conclude. Now let us see if we can get some element c with that property or not. The function f is defined on a bigger set, and then we know that f is differentiable. F is differentiable here, and we are given 2 points. So f restricted to a comma b, it is a continuous function. Continuous function on a closed and bounded domain is bounded, and this will we have mentioned in the lecture notes. The one thing that I have not mentioned is the following: a continuous function on closed bounded domain is bounded, of course, that I have said just now, and it attains its bound, in the sense there is a point L1 belongs to a comma b such that f of L1 is the infimum of fx, such that, well, just pull it x belongs to a comma b. Similarly, there is a point L2 belongs to a comma b such that f of L2 is equal to supremum of f of x such that x belongs to a comma b. So this result I have not mentioned in the lecture notes or in the video. Maybe I will add in the lecture notes in the continuous function part. We know for sure if a function f is continuous on a closed and bounded domain, it is bounded. So there so it is bounded. What extra we are saying here is there are points which attain the bound, the minimum and the maximum. So there are 2 points. So we have L1, that is that's taking the minimum value, L2 that's taking the maximum value. Suppose in the very simple case L1 is equal to A and L2 is equal to B. What does this say? This says A is the point where that has a minimum value, and B is that point that has a maximum value, but we know FA is same thing as FB. So this says if it's constant function, again in constant function you know the derivative is 0. So this case is a very simple case, that is because we know we are given that if A is equal to FB. Because of this implies f is constant function. For constant function, you know the derivative is 0, that we have already said before. So now the other possibility is L1 and L2. L1 is actually element of A comma B. It's not equal to A, not equal to B. So this says what? This says L1 is point of local minimum, is point of local minimum. Again this implies we have mentioned here, if I have a point of local minimum, the derivative is 0, f dash of L1 is equal to 0. Similarly, if you take L2 in this open interval A comma B, L2 is point of local maximum. Maybe one thing I need to mention here is, if this is the case, then this is called global maximum, in the sense there is no other point. In the sense maybe I'll talk about global maximum maybe in a other lecture, but here this L1 and L2 are local. We only have local description for at L1 and L2. In any case, the derivative is 0. So there is some point in open interval A comma B at which the derivative is 0. So the result is the following. So given a differentiable function f from u to r, suppose there are 2 points A and B such that fa is equal to fb, then there is an element c belongs to A comma B such that f dash of c is 0. So this is called the Rolle's theorem. So this very simple looking theorem is useful at many places, and we will see one very obvious result, very obvious application of this. So what we have is the following: f from u to r is such that there are 2 points A and B with this property. This implies there is an element c belongs to A comma B such that f dash of c is 0. Now suppose let us take some other function, again I am writing as f only, but not with this property, that we do not know whether f of A is equal to f of B. Now but if this is the case, then we have some interesting result. If that is not the case, see this trick you will come across multiple times when you study more mathematics. Whenever you have a nice situation and a corresponding nice result, and then as a next step you try to generalize it to a different situation, that this function does not have this property, but from this function we consider a new function which has this property. So, G is from U to R, we consider this function with some nice property for which G of A is same thing as G of B. For that function there exists a C with G dash of C is 0, that might give you some nice result about this function. Right? Let us do that. So, the way we are defining Gx is the following. So, we are defining Gx is equal to Fx minus Fa minus Fb minus Fa by b minus a x minus a. Now, so here observe that this is constant, there is nothing you need to worry about, this is constant and this is also constant. So, this G the differentiability depends on differentiability of f and the differentiability of this multiple of the identity function. So, this says this function G is differentiable. Let us check what is value of G of A. What is G of A? If I put A here, it is 0, so this is gone. If I put A here, it is f of A minus f of A, so that is 0. Let us check G of B. What is G of B? This is B minus A, and so this is gone. If I put B here, Fb minus Fa minus of Fb minus Fa, so these two get cancelled, again that is 0. So, so now we are in the previous setup. We have a function f from U to R such that there are 2 points A and B with this property. There should be some element C such that the derivative is 0. Here we have the same thing. We have a function G that is differentiable and there are 2 points A and B such that Ga is equal to Gb. This implies there is a C belongs to A comma B such that G dash of C is equal to 0. What is G dash of C? This is constant, so the derivative is 0. This part is constant, so the derivative is 0. So, whatever is remaining is G dash of x is equal to f dash of x minus Fb minus Fa by b minus a, and the derivative of x is 1, so I am not writing that. So, this says there is a point C here such that G dash of C is 0. So, I put C here. Similarly, this is and this does not have x part, so there is nothing to change here. And what we are saying is that this is 0, right. So, this is same thing as saying f dash of C is f of b minus a, f of b minus f of a by b minus a. So, this says suppose I take a differentiable function and a comma b are elements of U, then there is a point C belongs to a comma b such that f dash of C is f of b minus f of a by b minus a. So, this is generalization or an application of what we have seen before, the so called Rolle's theorem. Suppose we know Fb is equal to Fa, then f dash of C is 0, that we have already seen. So, this can be seen as generalization of the Rolle's theorem, and this simple looking observation has a theorem, has a name, it is called mean value theorem. And yeah, that is where we stop this session. In the next session we will see maybe some applications of the application of this theorem, and maybe some more examples, and that is all for this session.